Hello and welcome back, everyone. Today's lecture is all about water and why it's biology's favorite solvent. Now, water is definitely one of those compounds that people, especially chemists, sort of take for granted, but I hope to convince you all that for such a simple molecule, water is actually pretty cool. And we can learn a lot about its properties just by examining its structure, and then we can deduce why these properties uniquely suit it to make life possible. But first, let's do our class starter. The molecule of the moment today will be lauric acid. It's also known as dodecanoic acid. It's a simple fatty acid. It's the primary component to coconut oil, and it's commonly found in the formulations for soaps and cosmetics. And as you'd imagine from its molecular structure, it's not exactly soluble in water. It has a lot of these carbon components to it. Now, when you add it to water, this lauric acid, what it's going to do spontaneously, it's going to undergo this collapse of sorts automatically. And as it collapses, it's going to form these nanoscopic fat balls shown over here. And these are called micelles. And these micelles become suspended in the water that surrounds it. I want you to examine this process that occurs from the perspective of entropy. I want you to ask yourself, how does the entropy change for the quote-unquote system? And by that, I mean the lauric acids, the fatty acids. How does its order change through this micelle assembly process? The next thing I want you to ask yourselves is, how does the entropy change for the surroundings, which would be the water molecules that are suspending the micelle? The last thing, I want you to put it together. What is the net entropy change for the system and the surroundings all together? Everything, okay? Is delta S for each of these three items going up or going down? That's what I mean by entropy, okay? So pause the video and work this out independently, and then we're going to review the answer in class. This burial, this ordering of nonpolar solutes in aqueous solution is called the hydrophobic effect. All right, and notice how I made that turn pink? That means it's very important. The hydrophobic effect will pop up time and again because it makes so much of biochemistry possible. It is the reason why order appears spontaneous. The hydrophobic effect is the reason why the hepatitis A virions were able to spontaneously assemble as described in the previous lecture. It's the reason why in our molecule of the moment, the micelles were able to form that ordered structure spontaneously. We're not breaking the laws of thermodynamics. We're not creating entropy out of thin air. We are stealing entropy from the water around it. The disorganization of the water is what orders nonpolar solutes that are suspended in it. And it's all based off this process of burying the hydrophobes, aka inducing a hydrophobic collapse. That is the driving force behind ordering membrane assembly. All right? This membrane, it's basically a 2D micelle. All right? Think of it that way. It comes together on its own because of the hydrophobic effect. We will also be discussing at length how the hydrophobic effect is what prompts protein folding. It's also what governs a drug or a hormone or what have you binding its receptor. It's all about burying hydrophobes. That is what drives the entropy lowering appearance of biology. As budding scientists, I want to get you all into the habit of asking the question why. I told you last slide that water is able to engender the hydrophobic effect and spontaneously order and assemble nonpolar solutes. Well, I want the question to be asked next is, why is that the case? I want you to ask, why is water so special? Why is it so good at enabling the hydrophobic effects? Well, in my opinion, there are 4 reasons why that's the case. And to unpack that, I've redrawn that micelle that we introduced in our molecule of the moment in a way that I think highlights the 4 attributes of water that make the hydrophobic effect possible. So what I would like you all to do is to pause the video and think for a minute what you think the 4 properties are based off of this drawing, and then unpause to compare your answers to mine. So I'll wait a second, let you think, and now let's dive in. When I'm looking at this graphic, what I'm seeing is that these hydrophobic yellow regions, that's not yellow, these hydrophobic yellow regions are separated from the very polar regions surrounding it at large. Okay? And the reason why it's polar is because, well, water is highly polar, which seems kind of obvious, but it's actually really important that the solvent prompting the hydrophobic effect is extremely polar. Now, the hydrophobic effect, in essence, is all about disordering the solvent to order the solutes. So we need to have a solvent that has a high propensity for order. And that's manifested through the hydrogen bonds. All right, if you remember from the molecule of the moment, look at all those hydrogen bonds that were surrounding the micelle. A lot of them were shed in the process of assembly, and that allows this process to happen spontaneously. So we need to have a solvent that's very prone to hydrogen bonding in order to be a good source of order. Third, we need a solvent that has a nice liquid range. Okay? The solvent, and again, this feels kind of obvious, but liquidity is an entropic sweet spot, if you will. It's fluid enough where things can rearrange and assemble and disassemble, but it's not going to be so stiff and rigid like a crystal where it's not at liberty to do any kind of global motions. And it's not a gas, which is just so chaotic and so entropic that there's really nothing to work with. The last thing, and this is, in my opinion, the most challenging facet, is that water is ionizable. Okay, let's take a look at the surface of this micelle. It's covered in a negative surface charge. So it's important to have nonpolar solutes with regions that hate water, but you also need regions that would be tolerant and highly soluble in water that can generate a solubilizing face for whatever assembly is being formed. and that is occurring via the ionizability of the carboxyl groups at the ends of the lauric acid. It's not the right number of carbons, but we need to form this charge, and water is essential for allowing that process to happen. And we're going to unpack all of this in the slides to come. First, let's dissect polarity. I can't think of many liquids that are more polar than water. To refresh, a compound is going to be polar if it consists of highly electronegative atoms, such as oxygen, that are bound to electropositive atoms, such as hydrogen, in an asymmetric arrangement, okay? In a way that's going to create an uneven distribution of positive and negative charges throughout the molecule. And we can see that happening in this electrostatic potential map of water, where the negative electrons gravitate towards the oxygen, exposing the positive nuclei of the hydrogens, and that in turn generates our dipole moment facing the oxygen atom. Okay? Now, how polar is this water molecule? We know it's polar, but how does it rank amongst other chemicals? To help you get a feel for that, what I've done over here is reproduce just a part of a solvent polarity index table. And what this means is the higher the polarity index is for a substance, the more polar it is. And water is consistently, one of the highest ranked polar molecules. Its polarity index is 10.2. Okay? And there's really not that much north of that. It's the things that are frankly quite exotic. The closest entities that approximate water's polarity are strange compounds like dimethyl sulfoxide, which is a 7.2, dimethylformamide, that's 6.4. Ethanol, we all know ethanol, that's 5.4, okay? And everything beyond that is frankly not worth mentioning. So part of appreciating water's unique ability to sustain life, to allow the hydrophobic effect to occur, is understanding why these other solvents all fail to do so. I'm saying we need a polar solvent for life, so why are these guys not polar enough? It all comes down to elemental composition. Let's zoom in on the lauric acid molecule. At first, you're going to see the aliphatic chain most likely, and you may say, hey, that looks very nonpolar, and you would be correct. However, we cannot ignore the carboxyl group that is on the head of the lauric acid molecule. This is not only a very polar functional group, but it's also going to be charged when it's in water, which means it's not only polar, it's superpolar. So a more accurate word to describe the overall hydrophobic lauric acid molecule is that really it's an amphiphile, which is a compound that has both hydrophobic and hydrophilic components to it. Now let's examine these still polar but not as polar as water solvents, such as ethanol, alcohol. These have polar hydroxyl groups, and these will jive very nicely and dissolve the polar heads of the lauric acid molecule. However, they also have aliphatic regions on it. And these will commingle very nicely with the aliphatic tail of the lauric acid. Said another way, ethanol is also a little bit of an amphiphile. Water is absolutely not. It is just plain polar. So what happens if you were to add ethanol to a micelle water? Well, there's going to be a profound disassembly effect because the ethanol molecules, they're going to worm their way in and they're going to dissolve all regions of the lauric acid, the red polar surfaces and the hydrophobic yellow tails. And that's going to result in a scrambling event where delta S skyrockets for the system and also the surroundings. And we no longer have this nice micelle. We disassemble and no longer have a clear division between, inside and outside in the lower delta S version. All right. You add this to a protein, alcohol, you're going to scramble and denature the protein. You add it to a cell, and guess what? You're going to disassemble the cell membrane and get rid of a lot of essential order. This is how hand sanitizer kills microbes, by the way. Most polar molecules can't harbor the hydrophobic effect because they're just a little bit amphiphilic. I'll repeat from last slide though, water, however, is not amphiphilic. It has strong preferences about what it dissolves, such as ions, for example. Water has a very large dielectric constant, and that's a fancy word used to describe the ability for a substance to surround and insulate a charge. Ions have numerous critical biological functions, like neural action potentials, membrane potentials, etc. If water didn't have a high dielectric constant, it wouldn't be able to dissolve and hydrate these essential electrolytes, and they would just precipitate out as crystalline solids and be useless. Even micelles and lipid membranes have a surface charge that helps to suspend the agglomerates, and that will prevent them from, fusing together infinitely and merging into one giant cell, pretty much. To give you a feel on how charge-happy water is, we have an additional component to our solvent polarity table where we will map out the dielectric constants of the example solvents that I've provided. And if you're curious, 15 is considered, a very soft cutoff for what is considered ionophilic and what is not considered ionophilic. And ethanol, dimethylformamide, and DMSO, these are all very weakly ionophilic. Water, its dielectric constant is 80. That's about twice of what the second place DMSO gets. So water is really polar and really good at dissolving charged things too. The next property on our list is hydrogen bonding. Why does water have such a great propensity to be a hydrogen bonder? I know Gen Chem was not yesterday, but it does not hurt to remind you that the covalent bonds that we see here and here between oxygen and hydrogen, those are not hydrogen bonds. Hydrogen bonds are not bonds. Not covalent bonds at least, but rather they are intermolecular forces. Specifically, they're a special kind of intermolecular force, stronger than your average dipole-dipole interaction, because it is between one of the three most electronegative elements, fluorine, oxygen, and nitrogen, and it occurs through space when they are in proximity to a separate discrete hydrogen atom that is bound to either a fluorine, an oxygen, or a nitrogen. Okay? In the case of water, we have oxygen bound to two hydrogen groups, so it has two hydrogen bond donors. And since the oxygen has two lone pairs on it, each lone pair will serve as a potential hydrogen bond acceptor, which means maximally water can form 1, 2, 3, 4 hydrogen bonding interactions with itself at least. And when it does so, it's going to form this tetrahedral arrangement, which sort of looks like a pyramid. All right. Sometimes we call it a tetrahedron. Now, just looking at that tetrahedron, it looks quite ordered, meaning water, through its hydrogen bonding capabilities, is a good source of order that we can transfer to a biological system. Now, I got a question for you. What about ammonia, NH3? Ammonia is a very polar molecule. It has not two, but three hydrogen bond donors. And it also forms these highly ordered tetrahedra under optimal conditions. So why not, to at least general knowledge, has life formed in an ammonia environment yet? Well, the first strike against it is that ammonia is actually quite toxic. It's also quite basic. So we're going to talk about basicity and acidity later. But disregarding those two strikes, we also need to realize that not all hydrogen bonds are going to be the same. All right? Let's look at the relative strengths between the hydrogen bonds in ammonia versus water. As an outgroup, let's just consider the strength of a covalent bond. A carbon-carbon covalent bond has a bond enthalpy of about 500 kilojoules per mole. Okay, this is a measurement of how strong the bond or interaction is. Now, let's compare this to a non-covalent interaction, like the hydrogen bonds between two water molecules. Its bond enthalpy is much smaller, at 21 kilojoules per mole. Now, this is significant in the scale of intermolecular forces, and we need to compare this next to the ammonia-ammonia interaction, which has a bond enthalpy of 13 kilojoules per mole, which may look like, well, it's roughly the same, but this is only 66% of the strength of the hydrogen bonds found in pure water. And that's because nitrogen is less electronegative than oxygen. Something else that also factors into here is that water has a nice 2-to-2 balance of hydrogen bond donor and acceptor, and this one's a little bit more skewed to be 1-to-3. Ammonia only has one lone pair. So factoring all this together, water has great cohesion. Water's impressive cohesive forces explains a lot of its behaviors compared to other first-row hydrides. Its ability to form very strong hydrogen bonds and the ability to form up to 4 of them lead to the following. First, water has a really high melting point, okay? Let's compare this to first-row hydrides like ammonia, again, and hydrofluoric acid. These are going to melt at pretty cold temperatures. We're talking way south of, 0 degrees Celsius. All right, water melts at 0 degrees Celsius by definition. Water also has a really high boiling point, which is, again, a property of its intermolecular forces. It boils at 100 degrees, which is way farther out than both hydrofluoric acid and ammonia. Now, this combination of having a high melting point and an even higher boiling point is what gives water a very wide liquid range. Okay? Ammonia does not have as wide of a liquid range. And hydrofluoric, well, that has a comparable one, but let's put a pin in that for a second. But let's just take a moment to emphasize why a high liquid range is important, okay? It is, again, the entropic sweet spot. More on this later, but I'll just quickly say that solids are too ordered to react, which means metabolism can't happen, so ice is out of the question. And gases are too disordered because everything is flying around. Now, two other important properties that are founded through water's hydrogen bonding capabilities is surface tension. And this is really important for things like capillary action, which is essential for plants on our planet. All right, winding back to general biology, you may remember that plants contain these special tubes called xylem, which are essentially extended straws that run through the roots, the stems, and the leaves of all plants. And they don't really suck up water from the ground like straws through a process of negative pressure, but really it's the surface tension that draws water up through these channels. It forms these chains of hydrogen bonding interactions with itself and the cell walls. And that helps the water crawl up from the ground, up the trunk, and through the leaves. And you may remember this process is called evapotranspiration. And without that, you can't have plants. So if you don't have that property in water, all plants wilt and die, and terrestrial life becomes impossible. Specific heat is another property that correlates with a substance's strength of intermolecular forces. If you forget what specific heat is, it's the amount of energy needed to change the temperature of 1 gram of something by 1 degree Celsius. Every substance heats or cools at different rates, and you've observed this. It's summer. You go stepping on the beach, the sand burns your feet, and the water gives you frostbite. Both were exposed to the same amount of sun. It's just that one of those entities has a higher heat capacity and the other has a lower one. Do you know which one has the greater heat capacity? Water's heat capacity, which is denoted as C, is 4.18 kilojoules per gram per degree centigrade. The answer is water. Water has the higher specific heat capacity. Sand has a specific heat, I think it's like 0.5, very small. So it does not take a lot of energy to heat up sand, but it takes way more energy to heat up water. Said another way, as it cools, it releases more energy. Now, let's play devil's advocate. If I'm saying water has a high specific heat because of its strong hydrogen bonds, then hydrogen fluoride should work because it technically has an even stronger hydrogen bonding pair because fluorine is more electronegative. But we can't forget that hydrogen bonds in hydrofluoric acid cap out at 2 per molecule. Water can do up to 4. and you can see this reflected in its specific heat. Water's specific heat is unusually large. That's a big number for specific heat. Hydrofluoric acid, its specific heat is 0.014 kilojoules. You look at the wrong way, and it's going to jump 100 degrees in temperature. Okay? So this is important because water heats up very slowly and cools down very slowly as well, said another way. And that's important for buffering temperature. Large bodies of water, like the ocean, buffer dramatic temperature changes, and this helps everything on the planet stay within a sliver of water's liquid range. I'll reiterate, if the temperature gets too hot, enzymes will fall apart, membranes will melt, and you die. If things get too cold, the cells freeze, reactions stop, metabolism stops, cells rupture, you die. You can see this temperature buffering effect with weather data. In this chart over here, I plotted the average temperature of two areas that are roughly on the same latitude in America. We have, where I currently am, Long Island in blue, and Omaha, Nebraska in red. Let's look how the average temperature changes over the span of a year. Notice how Long Island, which is in blue, tends to run a little warmer in the cold months and a little cooler in the hot months, compared at least to landlocked Omaha. That's because Long Island is sitting on the Atlantic Ocean, which is serving as a heat sink in the summertime and a heat source in the wintertime, making the conditions a little bit more mild. Let's move on to the third property of water that makes it so good at fostering the hydrophobic effect, and specifically that is its liquid phase. Now there are going to be some pretty drastic changes in its properties as we progress from solid water ice to liquid water. Most subtly, those hydrogen bonds between liquid water molecules are going to be incredibly transient. Each hydrogen bonding interaction, which I'm representing here as just these jumble of dotted lines, they're only going to last 10 picoseconds, okay, before breaking, tumbling, and reforming with a different water molecule. 10 picoseconds is a blink. That is a trillionth of a second. Now, because these water molecules are tumbling at such a fast rate, they can't maximize their number of hydrogen bonding contacts. So on average, in any given snapshot, each water molecule is going to form only between 2 and 3 hydrogen bonds max with nearby partners. This changes as we progress from liquid to solid. In ice, the lower temperature causes molecular tumblings to slow down, and as a result, the hydrogen bond's half-life is going to increase from 10 picoseconds to 10 microseconds. That's a millionth of a second. Now that's quite fast, between you and me, but compared to a trillionth, that's a million times slower. Because the molecular motions of each individual water molecule have decreased, that allows them to maximize their hydrogen bonding contacts And when you iterate the tetrahedron hydrogen bonding network, you get the iconic hexagon shapes that are the hallmark signs of snowflakes and whatnot. And that's a result of being able to form all maximum 4 hydrogen bonds at each given water molecule in each snapshot in time. This has a pretty significant impact on the density of water because this large jump in the number of hydrogen bonding interactions, that's going to actually force the water molecules apart a little bit. So the density of ice is about 10% less than the density of water, 1 gram per mil versus 0.917 grams per mil. And the fact that the density of ice goes down compared to its liquid state, that's really peculiar. Here's a list of substances where its liquid density is greater than its solid density. We have water, like we discussed in the previous slide, acetic acid apparently, and I had to dig around the internet, but apparently gallium and silicon are also less dense as solids than they are as liquids. And frankly, none of these compounds, except for water, seem like good solvents for life. So why is this important to have the density decrease when we go from the liquid phase to the solid phase? Here's a recap of how our oceans behave in the wintertime. All right, the air will get chilly, the top layer of water freezes, and that acts as a thermal insulator from the water underneath to the extra cold air at top. So life will persist happily underneath until the ice thaws come spring. Now let's pretend we lived in a world where water was magically more dense as ice than it is as liquid water. And this is the behavior of most substances. When a cold front comes in, ice will form. And because most solids are more dense than their liquid counterparts, it will sink to the bottom of the ponds, the ocean, what have you, as a block of ice, exposing another layer of liquid water to the cold front, sweeping through, freezes it, falls back down. And this process repeats until the ice piles up and we have completely displaced all aquatic life. So now aquatic life is over after one winter. Everything is dead. And if it weren't for the peculiar fact that water is less dense as a solid, that would have completely thrown a wrench into evolution, and I think frankly would have made life impossible. The final property of water we'll be discussing is the most intense, so it's going to take the rest of this lecture and all of next one to fully appreciate, but that property is ionizability, aka water's acidity/basicity. If you were to obtain an ultra-pure sample of water and you wanted to quantify how many ions were in it, you would stick in a probe and measure its conductance. And if you were to do that, you would get a small but measurable reading of 0.055 microsiemens per centimeter. If you're curious, if water had 0 ions, that value would be 0. So this proves that water does ionize. The question is, to what extent does it ionize? Now, you may remember from general chemistry that water can autoionize through the following chemical process. Two water molecules can collide in a certain way to yield one equivalent of H3O+, which is hydronium, and one equivalent of O-, that's hydroxide. And this process is reversible, goes both ways, which means it's in equilibrium. And we can measure if equilibrium favors the production of products or reactants by assessing its constant K. All right? And the constant K is defined as the concentration of products raised to the power of their coefficients over concentration of reactants, also to the power of its coefficients. And in the case of water, let's apply this generic formula to this autoionization process. Plugging and chugging it in, the products are H+, which I often treat as synonymous with hydronium. That's quote-unquote acid. Concentration of hydroxide, that's quote-unquote base. All divided by the concentration of water. That would be the reactants. Now, from this conductance experiment, we can convert that value of 0.055 microsiemens per centimeter to a concentration. And thanks to that, we know that the concentration of hydronium equals 10 to the power of -7 molar. All right, that's an incredibly small amount. But hey, we know a variable now to enter into this equation. We also know that when water is pure, the concentration of H+ equals the concentration of O-. So that means we know this term and this term. We are almost at the point where we can solve for Ka. The last thing we need is this concentration of water. Now, this is where a lot of things go haywire. At first, it may seem sort of paradoxical. What is the concentration of water in pure water? We're used to thinking of like, what's the concentration of sugar in this solution of water? It seems a little bit strange, but there is a way to calculate the concentration of water in pure water. All right, the way you do that is, let's pretend that you have a liter of water, okay? And concentration is going to be moles per liter. So let's put 1 liter in the denominator position. And 1 liter of water, we know, is 1,000 grams, because the density of water is 1 gram per milliliter. We need to convert grams into moles. So we do that by multiplying it by the gram formula mass of water. And that's 1 mole corresponds to 18 grams. The grams will cancel out. So we can reduce this to 1,000 divided by 18, and that will equal 55.5 molar. That is the concentration of water in pure water. So you would think it's as simple as plugging in the variables and chugging out the answer, which is Ka. And I'll remind you, what we're trying to do is find out what equilibrium is like for water's autoionization. Are we favoring products or reactants? Is this a big number or is this a little number? All right, so it seems like a fairly straightforward bit of math. I'll just reiterate over here that Ka equals the products multiplied together. So that would be 10 to the minus 7 molar times 10 to the minus 7 molar. Oops. That corresponds to the concentration of water and hydroxide. And next, we are going to divide this by the concentration of water, 55.5 molar. And so when you do that calculation, you're going to get 1.8 times 10 to the negative 16 molar. All right, and that is what Ka equals. This is wrong. So many biochemistry textbooks do this calculation, and it is deeply flawed. So sorry for the red herring, but I'm now going to explain why this seemingly sensible approach to solving for Ka is incorrect. A tiny but crucial detail in these equilibrium expressions is that we're actually not dividing the concentration of products by their reactants. We're actually dividing their activities, okay? And the chemical activity of a solute equals its concentration only when it's dilute. Let's say 1 molar or less. So 55.5 molar is not dilute. It's super concentrated. So I don't expect you to know why, but when we're dealing with very concentrated entities in equilibrium expressions that are like 55 molar, the appropriate thing to do is to express their concentration as unity. Their activity approaches 1. So let's plug that in to a new attempt at calculating the equilibrium expression for water's autoionization. So the first thing we're going to do is we're going to call this actually Kw now because that's proper. And we're going to substitute in the chemical activities. It's still equal to the concentration, it's products over reactants, H3O plus times OH minus, all over what are the reactants. Last slide, we listed it as water, and that's true. But actually, another mistake that's really common is that it's actually 2 equivalents of water. It's water squared because 2 molecules of water will react with each other to ionize into H3O plus and OH minus. So that's another common mistake that gets propagated in these textbooks. All right, so now that we have the right terms in place, let's apply the correct chemical activities. The top part of the expression does not change because 10 to the minus 7 is dilute. It's going to be 10 to the minus 7 times 10 to the minus 7 molar. And the bottom, we're not going to put in 55.5 molar because that's ridiculous. Activity approaches unity, or 1, when very concentrated. And we're going to square that because there's 2 equivalents of water. And look at that. The units this time cancel out, which is a sign that we're on the right track. That didn't happen the last time. All right? So we're going to just simply multiply now 10 to the negative 7 by 10 to the negative 7, and we're going to equate that to 10 to the minus 14. That is the answer. That is the kW of water, or its equilibrium expression. So, what does this mean? It means because the kW for this equilibrium expression is so small that the products are greatly outnumbered by the reactants. The reactants, equilibrium favors the formation of the reactants. Hence, only a small fraction of water is ionized. That's what it took us the past 20 minutes to figure out from the equilibrium expression, okay? But that's a very important piece of headway. I do want to emphasize that I will not be testing you on the correct derivation here. I'm just putting this out there for future reference because a lot of smart scientists mix this up to this day. What you do need to know is that writing exponents is a pain, as you're starting to understand. So what we're going to do now is try to simplify this clunky math down a little bit further by expressing water's equilibrium constant as its negative log, which is called, the pKw or the pKa. And I'm going to show you how we do that. We are going to write there we go. pKw equals negative log of 10 to the minus 14. And the notation for negative log is basically that little p that we see here. Anyway, get out your scientific calculators and plug in negative log of 10 to the power of negative 14. And what you will get is 14. Pretty easy, right? Essentially, what the negative log of a term does is we put the spotlight on the exponents and we get rid of everything else. And we can do the negative log of pretty much anything. Remember how the concentration of hydronium is always 10 to the minus negative 7? All right? Shown there. Let's take the negative log of the concentration of hydronium to find the power of H, aka the pH. Doesn't that seem familiar? Negative log of 10 to the minus 7 equals 7. This is why we say the pH of water that is pure, that is neutral, is equivalent to 7. And the rabbit hole basically goes even further, because if the concentration of H plus is 10 to the minus 7 and the pH is 7, we know that at neutral, H plus equals OH minus, so the POH will also be equivalent to 7. And we can apply that to this equation down below, where the pKw, which is equal to 14, is equivalent to the pH plus the POH, which is at neutral, in standard conditions, 7 plus 7. Doesn't that work out nicely? This expression and this expression are really useful, and we will be using them a bunch, okay? And they are useful because the kW, it never changes. However, we can change the ratio of hydronium and hydroxide in a solution of water by adding in acids and bases. And to illustrate this, I'm going to direct your attention to the table shown on the right, okay? If we were to increase the concentration of hydronium ions in water to, let's say, 1 molar by adding in a bunch of Bronsted acid, what is happening to the pH? All right, the power of hydrogen is decreasing, which correlates with an increase in concentration. All right. At the same time, the hydroxide concentration, that's actually decreasing to compensate for the increase in H plus hydronium. And in doing so, we are maintaining water's pKa of 14. If you compare the exponents, no need to get your calculators out when the numbers are this neat and simple. 0 plus 14 is 14. 1 plus 13 is 14. 2 and 12 is 14, and so on and so forth. You can observe this at, in theory, any pH value. And because adding in external acid or base is shifting the ratio of hydronium to hydroxide, that means water is acting as either a corresponding base or an acid. And its equilibrium properties allow it to sample this wide range of pH values, which biology actually tightly regulates. Let's take, for example, physiological pH. All right, that's the pH of our blood cells, and also just of our blood and just our cells and tissue at large. If that changes so much as plus or minus 0.1 pH units from the ideal 7.4, that can be a recipe for death. Okay, just because water can sample all these pH ranges does not mean biology is happy to just let it go willy-nilly. On the other hand, let's consider specialized tissues such as the lining and interior of the stomach. Gastric juice, which is in our stomach, is very purposefully acidic. I'm talking a pH between 1 to 2 in most people. And think about it, having a very high concentration of hydronium ions, a very acidic environment, that can achieve many things. It can facilitate mechanical digestion of protein, it can sterilize incoming food, and that's all great until the next phase of digestion kicks in and the gastric juice passes down into the duodenum of the small intestine. All right? And guess what's lying in wait there? A bicarbonate buffered pancreatic juice, which has it's basic at pH 8 and lots of it to help quell the incoming gastric juice, which prevents your stomach from digesting and sterilizing the rest of your GI tract. So biology is constantly holding its finger on the scales of pH and only letting it tune or adjust when it suits some sort of physiological purpose.
So I hope we now have a greater appreciation on how water's properties underpin so many of its chemical behaviors. I'd like to end with a quick roundup summary of water's qualities and how those enable it to foster life. We left off with its ability to ionize, okay, and its ability to function as an acid or base is ultimately what lets it tune things like solution pH, yes, but also it's going to impart crucial surface charges to the acidic and basic surfaces of important things like membranes and proteins. Next, let's talk about the extreme polarity of water. First, that's going to allow us to dissolve the substrates of life. While ordering other substrates. And it orders them by causing them to hydrophobically collapse into intricate structures like membranes and proteins. And we can generate such ordered assemblies spontaneously because water has a lot of order to give. Water molecules form intricate hydrogen bonding networks and surround suspended solutes. Ordering the solutes that get surrounded is a spontaneous process because in doing so, that greatly disorders these interfacial waters. So the hydrogen bonding of water is source of order. To illustrate that point really briefly, we've got two separate solutes that are surrounded by, those x's, but when we combine them together, their surface area decreases. Which allows us to free up some water molecules that I've drawn as liberated x's over there. And lastly, water has a wide liquid range. And that is going to provide us an entropic sweet spot that enables all of the above. So therefore, out of the 350,000 compounds currently known to humankind, water has absolutely no substitute. And that makes it perhaps one of the most boring compounds out there to be rather special. Now, as for next time, we'll be diving in deeper into these topics of acids and bases, so I want you to get ready for that. But in the meantime, have a good one, everyone.